Good morning, guys. Today we are going to be talking about end behavior for our last topic for this week. And we need to learn how to describe end behavior. End behavior of a graph describes the values of the function as x approaches positive infinity and negative infinity. So we're talking about what happens as we go out the graph, what kind of values are we getting out of the function. So first we need to look at a little bit of notation. Here, this is for the case of positive infinity, right? So if we want to say, x is approaching big values going on the right side of the graph, this then would read x approaches infinity, positive infinity, right? X approaches positive infinity is how we would say that. Or here, if we're going the other way, the left side of the graph, we would say that x approaches negative infinity. So that's the first part, right? Is we want to know, are we going to the left or the right on the graph? And we need to look at polynomials and their degree, which, right, is the highest exponent. And we want to look at their leading coefficient. What is that number that is out in front of the first, or in front of that highest exponent, that if we remember from our definition was called a sub n. And that will help us determine its end behavior. It also helps when you're graphing a polynomial function to know about its end behavior. It makes it a little easier to draw a graph. Okay, so you have two options for this leading coefficient. It's either positive or negative, right? So whatever is that value that's out in front of our largest variable, if it's positive, then the right side of the graph will go up, and if it's negative, the right side of the graph will go down. So if we have a positive function, it's going to be something that's looking like this, where it's coming up. And if we have a negative leading coefficient, it could even be a parabola, right? But it's on the right side, it's going to be going down. Then when we're looking at our highest degree, it needs to be either even or odd. Because even functions, they have the left and the right side the same. So we could look at parabolas. We could look at what we call a quartic function that looks kind of like a W. And if we notice, both sides go the same way. We could have negative leading coefficients, and they would still go the same way on both of the sides, right? As we're going out towards negative infinity or positive infinity, both of these are going in the same direction. Whereas if we have odd, then the left and the right side are different. So we could have like the cubic function that looks like this, right? So on the left side we're going down, the right we're going up. That's what we're looking at, is this, what happens at the end of these graph pieces, right? When this keeps going, what direction does it go in? Okay, so if we have this chart is really nice, and I'm going to see if I can actually copy paste this into our assignment. But you could also jot it down in your notes. So here, if we've got that even degree and a positive leading coefficient, we'll have both sides going up. And if we've got that even degree and the negative leading coefficient, then both sides are going to be pointing down. If we have an odd degree function and we have a positive leading coefficient, if you notice, this is one of these where this is an increasing interval always, right? So as we're going off the left side, it's very negative, going down, and when we're going up the right, it becomes more and more positive. So if you notice, this is the opposite now if we've got the negative leading coefficient, where on the left side we're going up, and on the right side we're going down. Okay, so let's see if we can think about end behavior. So let's see, here we've got this first polynomial, 4x to the fourth minus 2x cubed plus 3x minus 3 equals 0. And we want to determine its end behavior. Well, our leading coefficient is positive, right? Here's my leading coefficient, 4. And it's positive. So we know that on the right side of this graph it's going up. That allows me to know that as x is approaching positive infinity, or the right side of the graph, right, then this graph of p of x is going to go to positive infinity. So this statement right here is your entire end behavior statement. This is what they look like. And we would read this. Sorry, I'm kind of going a little crazy with my highlighter there. This is as x approaches infinity, then p of x approaches positive infinity, right? And notice we do actually have to denote positive or negative infinity here. Now this is an even degree, right? If we're looking at the degree, that is this highest value of the highest exponent that we have. And then we get this statement that as since it's even, then we know it must have this where both sides are going up, right? It's this kind of a picture going up and up. So as x approaches negative infinity, then p of x approaches positive infinity, right? And this is what we call a quartic graph. So it looks, you know, something kind of like this. Here's another example. Let's look here at determining the end behavior of 3x to the 7th plus 8x squared plus 4x minus 13 equals 0. Here my leading coefficient is positive, right? Here's my leading coefficient. And it's positive, so I know that the right side is going to be going up. But the degree of my function is odd. Here my degree is 7. And because it's odd, then that means that the arms are opposite. It's this picture. But it is going up on the right side. So as x approaches positive infinity, then p of x approaches positive infinity. As x approaches negative infinity, then p of x approaches negative infinity. Because recall, again, even though it's not going to look exactly like a cubic graph, it would look something kind of like this. And it's kind of going to be going down on the left side and up to positive infinity on the right side. Again, this is not what the graph really looks like. It's just a very generic sketch. Okay, now we have a new example. And our leading coefficient is negative, right? It's negative 2. So this tells me that this function, at least on the right side, is going to be going down, right? Because we have a negative coefficient. And that allows us to make this statement, right? As x approaches infinity, positive infinity, going off the right side of our graph, then p of x must approach negative infinity, because this is a negative leading coefficient. Our degree is odd, so our end behaviors will be opposite. So if I'm going down on the right side because of a negative leading coefficient, then on the left I must be going up. It must be this picture, right? That I have an odd degree, the arms are in opposite directions. So since the first one, because we had a negative leading coefficient, said that as x approached positive infinity, then p of x is going to approach negative infinity. Well, if it's opposite, then as we go towards negative x, then p of x approaches positive infinity. Another example, here leading coefficient is negative, right? So that tells me we're going down on the right side, right? Right arm down. But our degree here is even. And since it's even, we know that both sides must match, right? Even functions have matching end behavior. So the leading coefficient is negative, so we know that it's going down, but we know that it's an even function as well. So that's telling me it's kind of this picture, right? It's both of them are going down. So here's our end behavior statements as x approaches positive infinity, then p of x approaches negative infinity, right? Right side going down. As x approaches negative infinity, due to the symmetry of even functions, then p of x is going to go towards negative infinity. I'm going to go ahead and skip a couple of my examples here. But I want to look at how we can use graphs to determine this leading coefficient. So here I'm looking at this, and I see, well, they're going in opposite directions, so this has to be odd. And as I'm going down on the right side, my leading coefficient must be negative, right? So we can see that here because this is going down, right? That implies that this must be a negative function. But because these are going in opposite directions, that also tells me that this is odd. So here we can really see this, right? As we approach positive infinity, right, going out this side of our graph, then my function values become increasingly negative. So p of x is approaching that negative infinity value. And that tells me that I definitely have to have a negative leading coefficient. Now coming off the other side, though, you can see as I approach negative infinity, I'm just going to keep increasing up off the top of my graph. So the graph's going towards positive infinity. So as x approaches negative infinity, p of x approaches positive infinity. And so since we have this opposite behavior, this must be an odd function. Another example of using graphs. Here I see both sides are going up, and they're both rising, right? As this value goes, as we approach positive infinity on the x-axis, my graph is climbing, it's rising. So that tells me I must have a positive coefficient, right? Since the right side is going up. But now when I look, both sides are going straight up. And we know that, well, for it to be odd, they have to go in opposite directions. So since we've got the same end behavior going on, right, as we go both to negative and positive infinity, we go towards positive infinity on the function values, or the y-axis, this must be an even function, right? So if they're pointing same direction, even, and it's up, right, so they're positive. If this graph was flipped over, that would show us a negative. Okay guys, that's the last of my examples for today. I'm trying to keep my videos relatively short for you. Please let me know if you have any questions.